So, welcome back friends. So, we were looking at interpretation of the Klein-Gordon equation essentially in terms of electric charge. How do you can interpret the phi to have an electric charge and phi star to be having a negative electric charge essentially. So, that you can only do by coupling with the electromagnetic field, and we introduced how to couple it with an electromagnetic field today. Okay. So, we introduced the electromagnetic theory Lagrangian, the Klein-Gordon field Lagrangian, and then we introduced something called the minimal coupling, through which you can couple the Klein-Gordon field or the Klein-Gordon phi with the electromagnetic field essentially, and with this we can re-express this particular thing in this particular fashion essentially. So, the total Klein-Gordon equation in the presence, which is in the presence of an electromagnetic field, will give you this particular fashion. Now, if we expand this, so you have del mu plus I e a mu dagger del mu plus I e a mu minus m square phi dagger phi minus 1 by 4 f mu nu f mu nu. Now, we can derive, okay, this is a straightforward expansion. Okay. Oh no, there should be a phi here essentially on both sides. So, did I put a phi here? Yes. So, there should be a phi here. Okay. Now, if we expand this essentially, now I can expand it this particular fashion, and what you will get are essentially several terms. Okay, and then we can take the equations of motion and then check what is the source terms for each of them essentially. Okay. So, you can do this exercise, okay, and this Lagrangian essentially is equivalent to del mu phi dagger del mu phi, okay, phi dagger del mu phi a mu I e, okay, and also there is another term which is essentially, okay, I e square phi, phi dagger phi a mu, and there are lot of other terms essentially, okay, plus other term. So, what I want is to concentrate on this particular thing plus Hermitian conjugate and so on, so essentially. So, let us concentrate on this term. So, this term if you see, if you remember correctly, is the current term essentially, is nothing but the current term. So, if you remember the current term, the current J mu, if you remember, okay, was given this particular fashion is equal to J mu is equal to phi dagger del mu phi minus phi del mu phi dagger. Okay. So, this is nothing but your Klein-Gordon current essentially. So, this current we interpreted as the difference between the charges essentially, that the difference between the currents of the positively charged particles and the currents and also the charges of the positively charged particles and the negatively charged particles. Now, you see this current is coupling with the electromagnetic current. So, this is actually the electromagnetic charge. So, this charge, if you take the 0th component essentially, this 0th component J mu, if you remember, has J bar, and J rho has the component phi dagger del 0 phi minus phi del 0 phi dagger. This, okay, couples to, this is nothing but the electric charge density, because now you see that this is actually coupling to photons essentially. This is coupling to this density, this electric charge density, it is can be interpreted as electric charge density because this is the one which is coupling to photons essentially. So, this is the one which is coupling to photons. So, we now our interpretation that rho should be interpreted as the electric charge density for, and J should be represented as the electric current density stands validated, because now you see that J actually J mu couples to A mu, which is nothing but the photon current. So, the A mu is the photon current. So, J mu A mu is nothing but kg current coupling to photon current. So, when does particles couple? Essentially current interaction. So, you have this is like an electromagnetic theory. So, this is nothing but charge current and charge density in the relativistic. Okay. So, with this I tried to convince you that, okay. So, with this I tried to convince you that introducing writing in terms of when this problem, the Klein-Gordon equation, which seems to be you do not have to throw it out completely, because it is not meaning it is not well defined, or it is not because of the current problem, and it has a probability interpretation problem. It should not be thrown out, essentially it should not be thrown out, because in a fully multi-particle theory. So, when you improve on when you replace the quantum mechanics in the relativistic regime to a completely field theory interpretation, in a completely field theory interpretation. So, what you end up having is that this current J mu is the one which couples to the electromagnetic field, and phi and phi star have can be shown to carry opposite charges, because they couple in the with the opposite minus sign, essentially they couple with minus signs which are opposite minus signs. Okay. So, phi and phi star will have, or phi dagger will have opposite currents. Okay. They have opposite charge densities, they have opposite currents, and this should not be interpreted as probability density, but instead as charge density and charge current density. Okay. So, I hope I have convinced you about this particular part essentially. So, before going further, just give me 1 or 2 tidbits about this Lagrangian, because we will keep using this essentially again and again. This is the Klein-Gordon Lagrangian in the relativistic sense, essentially with an electromagnetic field, but you see there are these two interaction terms or current terms. One is phi dagger phi, A mu. So, now this I will just introduce you two particular one particular component. Now, this is what this term represents. You can represent it in a graphical manner. Okay. Phi dagger del mu phi minus phi del mu, it can be represented in a graphical manner, and that graphical manner so, this can be represented in a graphical, the interaction between the phi and the photon can be represented in a graphical manner. So, you have an incoming phi and then there is a outgoing phi. So, there is an incoming phi essentially, and at a given space time point, because all of them are in the space time point, and which gives you an A mu essentially. Okay, which gives you an A mu, and this has a coupling minus I e essentially. I e is electric charge essentially here. Now, this is nothing but the Feynman diagram, the well known Feynman diagram. And the theory which we are looking at is something called the scalar QED theory, the scalar quantum electrodynamics. Now, normally ordinary electrodynamics, which we will see a bit later, is nothing but electron and a photon, a theory of electrons and photons, but here instead of an electron what you have is a scalar particle which does not have any spin. Okay. So, we have to represent it by a dotted index. Okay. So, this is how a scalar which comes with a given space time point at a given space time point, which is called the vertex. So, this is called the vertex. The particle comes in and the particle goes out, and while going at that point it emits, it interacts, it emits a photon, essentially it emits a photon because it is a charged particle, it emits a photon, that is a space time point, and that point is called the vertex essentially. That is a point which is called. So, this is the first example which you are seeing of a Feynman diagram essentially, of a Feynman diagram, and the theory which we are dealing with is called scalar quantum electrodynamics. There is also one more diagram, vertex diagram in this particular theory, in which a particle can come and go out. So, the particle comes phi, but it has 2 photons, it is higher order in field theory. So, it has a coupling which is E square essentially, it has a coupling higher order in the electric charge. So, it has E square essentially. So, it is next order in perturbation theory. These are important concepts which we will see. So, this is a diagram at first order in perturbation theory, and this is a diagram which is second order in perturbation theory. So, that means it is at the, so the perturbation theory is done in the number of times the coupling constant appears. If the coupling constant appear once, it is a first order perturbation theory, and if the coupling constant appear twice, second order, and higher and orders. Okay. So, sometimes the second order these are called tree level diagrams, the processes in which the coupling constant appears at each vertex with only first order with only one coupling constant is called tree level process essentially, and these are called loop level processes. These are called loop level processes essentially. Okay. So, this is the thing about. So, what we have seen are glimpses of quantum electrodynamics, which is important in understanding the Klein-Gordon field in a complete sense essentially. Okay. So, this is this is the interaction. So, there is a current. So, this diagram in which you have, so this is called okay, this diagram here is the current of the phi field. So, this diagram with dotted indices is called the current of the phi field, and A mu is the current of the electromagnetic field essentially. A mu is the current of the electromagnetic field. So, see here we had 2 electromagnetic fields currents essentially. So, it is represented by a curvy line like this particular fashion, in this particular fashion, in this curvy line, whereas the scalar is represented by dotted lines essentially, by dotted line. Now, when you have to compute it, it becomes easier when you are looking at process in which, say for example, if a photon is interacting with another photon or any other things, or a scalar particle, a spinless particle is interacting with electromagnetic interactions essentially with some other particle. So, you need to use these diagrams. The example of scalar electrodynamics is important to understand some fundamental particles called pions. Example, this is okay, right?
Yes, sir. Okay.
Example of theories, particles in nature following scalar electrodynamics are pions. Pions are particles, they are fundamental particles essentially, which are made up of quark anti-quark pairs essentially. Pions are made up of quark anti-quark pairs. So, these pions come in 3 varieties: pi plus, pi minus and pi 0. This is a neutral pion. And pi plus and pi minus are antiparticles of each other. So, if this is a particle, pi plus is a particle and pi minus is an antiparticle. Now, the question is essentially now, so you have pi plus and pi minus represented by a charge scalar field, that means because these are spinless particles, they are spin 0, mesons, they are pseudoscalar. We will forget about the pseudoscalar part a bit right now, for the present just forget about the point that it is pseudoscalar because it depends upon the parity. We will come back to it later on essentially at some when we are dealing with Dirac equation. Okay. So, pi plus and pi minus are represented by a scalar field. So, if this is a particle, this is an antiparticle. So, if it is represented by phi, this is a complex scalar. Then phi star would be representing antiparticle. If phi is representing particle, phi star will represent antiparticle. So, they correspond to a charged or complex scalar Klein-Gordon field. Klein-Gordon field, okay, Klein-Gordon wave function or Klein-Gordon field essentially. So, again, so because Klein-Gordon field has is a scalar particle, it does not have any spin, we will see that also in a bit essentially, but it has electric charge. So, that means it has to be complex, so that phi and phi star should represent different particles, essentially particle and antiparticle. So, they should different degrees of freedom. So, they should represent phi and phi star, they should be at least complex, okay. And so, you should have a complex scalar, and from writing the Klein-Gordon they satisfy the Klein-Gordon complex scalar field. Question: now what happens to the neutral pion? How do you represent the neutral pion essentially? Neutral pion does not have any charge. So, it is a neutral particle, it cannot couple to the electromagnetic field. So, it does not see because it does not have any charge, it does not participate in electromagnetic interactions, okay. It does not see the photon, it does not interact with the photon. How do you represent it? Can you use the Klein-Gordon equation again, okay? Can you still use the Klein-Gordon equation for the neutral pion also? The answer is yes, because the neutral particles are antiparticles of themselves. So, they only have one degree of freedom. So, if I impose phi is equal to phi star, that means phi would be a real field essentially or a real wave function. But let us stop, if in terms of the field theory language it is a real field. So, phi is a real field. So, Kg equation also can be used for the neutral pion, but instead of having it for a complex field, you have to use it for a real field. So, how do you write the Krejci equation for a real field? Exactly like that, but you have to be careful, because when you are deriving, okay, del mu phi minus m square phi square. So, this is the Lagrangian LKG. Okay, there is no dagger, nothing, there is no star and everything essentially. So, this is nothing but del mu phi whole square by this thing. So, if you derive, so you should put a half in front of this, because you should get the equation to be del plus m square into phi is equal to 0, where phi is real. Okay, I will rewrite it neatly essentially. So what, how do you represent it in terms of real field, but you should put a half factor in the Lagrangian. So, then in the Lagrangian there will be a half factor, because you have to avoid the double counting when you do the Euler Lagrange equations, because phi and phi star are not two different degrees of freedom. So, you put a half factor. So, you put del mu phi square minus half m square phi square as the Lagrangian, and this half factor will cancel the two factor coming in the equations of motion, which gives me del plus m square phi is equal to 0. So, neutral particles, spinless particles can be represented also by the Klein-Gordon equation. So, it is a very important equation. So, all relativistic particles, okay, neutral, charged, spinless, meaning which are all relativistic spinless, that means scalar. I will tell you why spinless particles are called scalars later on. Essentially, particles charged or neutral are represented by Klein-Gordon equation. So, what we learned today is that the Klein-Gordon equation is a very important equation, and then how we can represent the Klein-Gordon equations for charged particles and neutral particles essentially, and the interpretation in terms of charged particles can be understood by coupling it with the electromagnetic field, essentially how to couple it with the electromagnetic field, and we saw how to couple it with the electromagnetic field by using some technique called the minimal coupling. This is exactly what we do in quantum mechanics, but we just imported it to in the relativistic framework essentially by just replacing the vector to a 4 vector. So, we just made P from ordinary 3 vector to 4 vectors, and we use the same formalism, and then we got the interpretation why it is because we saw that the Klein-Gordon current now couples to the electromagnetic current essentially, which is given by the vectorial current A mu, okay, which contains the vector potential as well as the scalar potential. And so, this tells you that the Klein-Gordon equation can be the Klein-Gordon current, which we saw as not should not be represented or should not be interpreted as electric as should not be interpreted as probability current and probability density, but instead should be interpreted as electric charge density and electric current density. And we also saw finally how to represent neutral pions by using a neutral scalar field, which is the Klein-Gordon equation for a neutral particle which does not have any current charge current associated with it essentially. Okay. So, from next class we will see some other aspects of Klein-Gordon equation which are something like non-relativistic reduction, and then we will further go to spin half particles which are given by the Dirac equation. So, I will stop here.